Wow. Well, thank you very much, Lisa, for that lovely introduction. Thanks as well to Eric Ward, our VP for Public Programming, and our friends at Rainy Day Books for organizing this event. Thank you to John Ratliff, our Vice President for Communications, for publicizing it so well and filling up the auditorium, or the reading room rather, so nicely. And thanks to all of you in the audience here tonight and anyone watching over the internet for joining me. Out of curiosity, before we begin, I'd appreciate it if, are there any electrical engineers in the audience? Just raise your hand quickly. Okay, keep those up. Are there any chemists or chemical engineers? Good. How about physicists? All right, thank you all. Oh, anybody here work for RCA? I always check that now. All right, before I begin, just to make sure that we're all on the same page, I want to provide a brief disclaimer, especially for those of you with a technical background. So here it is. This is a historical discussion. I am not a chemist, a physicist, or an electrical engineer. My degree is in the history of science, so any of you who came here eager to hear about the relative merits of the anisylidine p-aminophenyl acetate derivatives that were used in the first liquid crystal displays, as compared to the cyanobiphenyls that later replaced them, well, I fear you're going to be dreadfully disappointed. Nevertheless, I hope that there will be sufficient technical content in this presentation to keep you engaged for the next 40 to 45 minutes or so, as we consider a fascinating case study in the history of American innovation. Now, today when we think about high-tech innovation, we think about firms like these, right? Google or Intel, Hewlett-Packard or Apple. Firms that benefited from the unique combination of venture capital, military funding, the presence of educational institutions like Stanford, and interconnected social and financial networks that really allowed Silicon Valley to become the epicenter of the American electronics industry. However, that wasn't always the case. Today's technological trendsetters may be based on America's West Coast, but I would argue that the electronics industry we know today emerged in the East, and specifically in the great state of New Jersey. Yes, before Silicon Valley, there was New Jersey. Now, most of you are probably familiar with Thomas Edison and his laboratories at Menlo Park in West Orange, where he and his colleagues developed the phonograph and the light bulb and all those other inventions that you heard about in school. If you know anything about the history of electronics, you probably also know about this building here. This is Bell Labs in Murray Hill. This is the birthplace of the transistor, Unix, the programming language, information theory, solar panels, and some of the first communication satellites all came out of there. These are the two best known, arguably, of the electronics research organizations that were in New Jersey, but they were hardly alone. Go up and down the state and you could find them all over the place, from the Weston Electrical Instrument Company in Newark to the U.S. Army Signal Corps labs in Fort Monmouth. But if you were a typical American consumer during the 20th century, none of these organizations had as much of an impact on your life as one run by the Radio Corporation of America, or RCA. From the end of World War I until the middle of the 1980s, RCA was the undisputed leader of America's consumer electronics industry. In 1926, this was the company that organized and launched the first radio broadcasting network, NBC. And under the leadership of its president, David Sarnoff, in 1939, they announced at the New York World's Fair that they would be launching the first regularly scheduled television broadcasts in the country. After that, shortly after that, during World War II, RCA opened a research laboratory of its own in Princeton. This was the birthplace of color television. Before the digital changeover that we all went through in 2009, this was where the color television broadcasting standard that we relied on came from. Later on, RCA scientists and engineers would develop a variety of new technologies that continue to shape our lives to this day, ranging from new and improved integrated circuit technology to the first ever blue LED. RCA Labs was also the birthplace of a now omnipresent technology that was unveiled to the public at a press conference in New York City, almost exactly 50 years ago. And that, of course, as you know from the introduction, is the LCD. And this is the leader of the project that made the LCD possible. His name was George Heilmeyer. And here he is demonstrating one of his displays in connection with this 1968 press conference at RCA's headquarters at 30 Rockefeller Plaza in New York. James Hillier, the vice president in charge of RCA Labs at the time, got up and explained that these new displays relied on a strange new set of substances called liquid crystals, and that these displays offered a variety of advantages over existing electronic displays. For example, unlike the big, bulky cathode ray tubes that were used in conventional televisions, these were very thin and light. They also didn't emit light of their own. You might be wondering what he's doing here. He's shining a spotlight at the display because it reflects light. It doesn't emit light. And that means it doesn't take as much power to run, which offers a wide range of possible applications. Imagine you could do things like have a portable clock or wristwatch. Maybe even, Hillier joked, a portable TV that you could take to the beach and in between bikini watching, actually watch the Mets figure out a new way to lose a ball game. Hillier closed the presentation by noting that the company hoped that LCDs will reach their full potential, and that when they do, you'll learn about it at a press conference, an RCA press conference, similar to this one. His prediction turned out to be half right. There's no denying that the LCD has reached its technological potential. For the past decade, it has outsold traditional cathode ray tube televisions. The LCD is the basis of a massive multi-billion-dollar global industry, and to give you a sense of its scale, think about all the things that have liquid crystal displays in them. Laptops, cell phones, wristwatches, calculators, you name it, right? Just looking at televisions, estimated sales in 2016 were over $83 billion. All right? And that's just televisions. So, the technology has reached its full potential, but RCA is not the one making the announcement about it. Because within a decade of the company unveiling the technology, they decided they were no longer interested in producing it at all, and they exited the LCD business. A decade after that, in 1986, RCA itself ceased to exist. They were sold to General Electric. So this is something of a paradox, right? Here we have a company that was the first mover in an industry that turned out to be very successful, and they ultimately were completely unable to capitalize on that position. This contradiction was fascinating to me when I first found out about it. And I learned about it over a decade ago when I was a graduate student at Princeton. I was in the history department. I was trying to figure out what I was going to write my second-year research paper on. And you need to find a source of primary documents, a set of archival materials. So I went to the nearest archive I could find that was related to my general area of interest, the history of technology. And that was housed at the old RCA labs. It's called the David Sarnoff Library. And I went over there, and you can see a picture of me standing in the reading room with some of the materials I consulted. And I started talking with the director, of the library, and I asked him what I should write about, and he said, "What about LCDs?" And I said, "Well, I know what LCDs are. What do they have to do with RCA?" And he said, "They were invented here." And I said, I had never heard that before. And he said, "Well, no one's really dug into the history of this in a sustained way. Maybe that would be a good project." So I started to dig. And the more that I went through these papers that were housed at this library, the more I found to intrigue me. Because this was a story of successful invention and failed innovation, right? They came up with the technology. It was there. But they were unable to transform it from a prototype into a product. They weren't able to accomplish the task of what we refer to as intra-firm technology transfer, moving from the laboratory into the factory. This is something that still is problematic for many firms today, right? How do you make that transition? For me, however, the big problem was how do you reconstruct that process? How do you figure out the various steps along the way from laboratory to factory? And particularly, how do you figure out what went wrong? Now, I could rely, and I was fortunate that there were, a variety of published sources. And these are the sorts of things you could actually find here at the Linda Hall Library. Here, for example, we have a journal article from the proceedings of the IEEE, the major electrical engineering organization. And this is from 1968. It explains how some of those early liquid crystal displays worked. And here's a patent that George Heilmeyer submitted, and it was issued in 1970. These are both really useful sources, but only for answering certain sorts of questions. Because if I wanted to figure out, for example, what inspired Heilmeyer to look at liquid crystals in the first place, I wouldn't necessarily find that in a journal article. Similarly, you wouldn't find if they made mistakes along the way or changed directions mid-course in the research. That's not included in a journal article. If they collaborated with people or were inspired by other sources, you wouldn't find that necessarily. There might be an acknowledgement section in a journal article. You definitely wouldn't find it in a patent, right? Because a patent is all about trying to stake out a claim for originality. So you definitely don't want to say where you were inspired or what drove you to pursue something. And again, this is both of these are telling stories about the product, not the process. They're telling the story knowing how it ends. I wanted to know how it looked all throughout. So, thankfully, there were records that I could use. RCA's archive was full of them. Here you can see a technical report, the sort of thing that would be issued every couple of months to let people know what was going on with a particular project. Next to it, you can see a page from a laboratory notebook, where they're actually showing off an early form of display. To give you a sense of how many lab notebooks I had a chance to read, see those books with the red covers? Those are laboratory notebooks from all the different scientists who were involved. They were required to keep them for intellectual property reasons and typically filled them in on either a daily or a weekly basis to let their supervisors know what was going on, what they were working on. Sometimes they were very neat, like this one. The handwriting in this one is pretty clear. Sometimes they were completely incomprehensible. But together, when you put them all in one place and looked at them over a long period of time, you were able to construct a very complicated and rich story. A story that I was able to further enhance through research at additional archives, like the Hagley Library in Delaware, which eventually inherited these materials when the Sarnoff Library closed in 2009, as well as the Science History Institute, formerly the Chemical Heritage Foundation in Philadelphia. I even went to Kent State in Ohio, which is home to the Liquid Crystal Institute, and looked at some papers there. And I also looked not just at print sources like this, but if you're a historian of technology, your primary sources are also artifacts, right? Because you can learn a lot about what was important or how they approached a challenge by looking at how objects are manufactured. So here you can see this is a very early flat panel display developed by RCA engineers that is at Wright-Patterson Air Force Base in Dayton. And we've tried to light up a couple of the pixels here. I don't know if that's visible from your seats. Even more than the artifacts, however, I was fortunate to be working on recent enough history that several of the people who were involved were still alive. And that was an amazing privilege, to get to sit down and talk with my historical actors and ask them questions. And in some cases, they had not just oral histories to share, but also personal papers, correspondence, photographs, all sorts of useful and previously unexplored documentation that allowed me to dig into this question of what happened to RCA's liquid crystal project from a whole new perspective, and one that I was really grateful to have. Because all too often when you talk about the history of corporate science, it's told from the top down, right? It's very easy to say, this is a management mistake, this is a management story. Someone at the top screwed up. But you don't often hear about where the scientists fit into the picture. And what my book really explores is the role of scientists and engineers in shaping corporate research decisions. Because when these managers are making those choices, they are not the ones with first-hand knowledge about how the technology works, right? They're not the ones in the lab tinkering. They're not the ones who put together the original displays. They go to the scientists and the engineers and the technicians, and they ask them, what do you think? Does it look like this is a possible application that we can use? Is this something that we could commercialize? What's the best way to do it? What's the most promising product we can put this into? And what you'll see, I hope, during the course of the next few minutes is that they were crucial to getting the LCD program started in the first place, and they also played a role in its conclusion. But you can't tell the story without both sides. You can't tell the story of corporate science without thinking about the scientists and the managers. And that's what I was trying to do. So, before we get into that, let's take a brief pause and ask a relatively simple question. Why would RCA care about making liquid crystal displays or flat panel displays in the first place? Well, just like today, The consumer electronics industry in the 1950s and 1960s was driven by obsolescence, right? If everyone goes out and buys a black and white TV, then nobody's going to want to buy any more TVs. So black and white TVs become obsolete. What do you need next? Color. And RCA, of course, was in a good position to deal with that because they invented modern color TV. But by the end of the 1950s and the beginning of the 1960s, color was starting to become popular. So what comes next? Well, David Sarnoff, who I showed you a picture of a little while ago, gave a speech in 1951 and then repeated some of what it said there over the years after that, that led people to believe maybe the next step would be a television that was flat, that you could hang on the wall. In fact, I found a 1959 ad from Popular Science that literally said, "How'd you like to hang your TV picture on the wall?" Now, this is a picture from 1960, and that's a pretty impressive setup. RCA was advertising these mural television cabinets. But here's the secret. That is a regular TV, and they cut a hole in the wall, and they stuck the TV in, and they made it look flat. Easy. And that worked out fine for the few people who were willing to pay to have someone come in and cut a hole in the wall the size of their TV. Now, there were some people who decided to take it another direction and actually tried to make a technically feasible flat panel display. Remember that display I showed you from Wright-Patterson Air Force Base a few minutes ago? Here's a slightly higher resolution version with one of the people who built it. Right? This gentleman's name is Bernard Lechner, and he oversaw the construction of this early flat panel display. 1,200 elements, pretty low resolution, but high enough that you could tell that it's him, right, in the picture. And this is an actual flat panel display. Monochrome, low resolution, but there's a possibility here. It's technically feasible. So people are thinking about this, they're talking about this. There's an understanding within RCA, if you could come up with a way to replace the big cathode ray tubes they were using in their televisions, that would be of interest to the company. Now here's the ironic twist. Liquid crystal displays, which would ultimately be the most successful approach to come out of RCA labs to make that dream a reality, the original research had nothing to do with television at all. Instead, it had to do with lasers. Here's George Heilmeyer again. This is a little earlier in his career. He graduates from the University of Pennsylvania, enrolls at Princeton in a PhD, and they had an arrangement with RCA where you could work at RCA and then pursue a PhD at the same time. He did his work on organic semiconductors with a specific interest in lasers, which were attracting a lot of attention at the time. As he said later, I wanted some of the action. And by that he meant he wanted to come up with a way to use his organic semiconductor research to figure out a new way to modulate laser light. Lasers were new. The thought was that you could use lasers in communication systems, but you need a way to modulate the beam, to alter its phase or its polarization or its power somehow. Now, up to this point, they had been using inorganic crystals, which were hard to grow and very inefficient in terms of power use, or both. And these organic crystals that Heilmeyer was working with, are there any organic chemists in the audience in particular? Organic materials, you could manipulate those in all sorts of interesting ways. And Heilmeyer thought this might be a solution to the problem. So he starts growing these large organic crystal ingots. They don't quite work. It turns out they're rather brittle, and when they get into contact with water, they tend to dissolve or break down, so that's not going to work. So instead, he comes up with another possibility. And you can see here a hint of what's going on. This is from his lab notebook from 1964. He says, you know, I am aware of a couple of different liquids that can affect the passage of a beam of light, particularly if those liquids have what are called polar molecules. So that means that they have a positive charge and a negative charge, and they're pretty widely separated from each other. So what if I put a dye, he says, into one of these polar liquids, and then I apply an electric field? Still with me? This is about as technical as this is all going to get. All right? So here we have these rectangular-shaped solvent molecules, the liquid, and the dye molecules are the circles. And if you apply a field, he says, they'll line up. Right? They'll line up with the field. And the dye will be in between the molecules. And maybe that will cause its absorption properties to change, how it absorbs light. Maybe that'll be affected. Either because there will be what's called a Stark effect, that is, the electric field on the molecules will be so strong it'll actually split the spectrum, or the dye could be a special kind of dye that changes color depending on its physical orientation with respect to polarized light. So one or the other. And he tries it. He gets one of these compounds that he's really excited about. It's called nitrobenzene, and he mixes it up, and he tries the experiment, and it is a complete flop. He needs something that will rotate his dye molecules differently. And this ultimately leads him to liquid crystals. But before I can explain that, what are liquid crystals? I feel like I've been talking about them for a while, and I haven't told you what they are yet. So, let's jump back in time to the year 1888 in Prague. And this guy here, Friedrich Reinitzer, an Austrian botanist at the Institute of Plant Physiology at the German University, who was studying carrots. And specifically, he was interested in figuring out the formulae of all the different compounds you can extract from carrots. One day, he's working on a compound called cholesterol benzoate, which is related to cholesterol, but it's a derivative of it. And he's doing what you normally do in a chemistry lab. You try to figure out the physical properties of it. And step one is you figure out basic physical properties like melting point. So you take a piece of the solid material, you put it on a heated stage, you heat it up, and it should turn into a liquid, right? Easy. Except not. Because when Reinitzer did this, he noticed something strange. When he heated it up to a certain point, it melted, but it turned into this kind of cloudyish liquid. And then as he heated it further, the cloudiness went away and eventually turned into a clear liquid. That's strange. And then, when it cooled off, it went back. This was reversible. This did not make sense. Compounds have one melting point. That's what they're supposed to do, solid to liquid. It's pretty straightforward. Here we had something that seemed to have two. So he contacts a crystallographer and chemist named Otto Lehmann, who decides he's going to study Reinitzer's crystals using a special microscope he's developed with a heated stage, so he could heat it up between those two melting points and look at it when it's still cloudy, and look at it with polarized light. Because if you're looking at crystals, that's really useful. It'll affect the polarized light in specific ways. And he sees really interesting patterns kind of like this one here, which suggested something unexpected. Clearly we were dealing with, he said, something that can flow like a liquid, right? It could take the shape of its container, it poured and flowed, but it had the optical properties of a crystalline solid. It affected light just like a crystal would. So he referred to them, creatively enough, as fließende Kristalle, flowing crystals. And later he referred to them as flüssige Kristalle, liquid crystals. By the way, if you'd like to learn more about Otto Lehmann, we just acquired a large collection of his publications here at the Linda Hall Library, and I highly urge you to check out our latest issue of The Hedgehog, our newsletter, where I've written a short piece about Lehmann and his work. Okay, shameless plug done. Let's put that down. Now, Lehmann comes up with this explanation. There's a flurry of interest before World War I and even during the interwar years, but after World War II, liquid crystals were more of a laboratory curiosity. There was very little interest in any sort of industrial use for them in particular, but they did capture the interest of at least one physical chemist who happened to be a colleague of Heilmeyer's. This gentleman here, Richard Williams. Williams was a graduate of Harvard University, and while he was there, he had studied physical chemistry, and he knew about liquid crystals from textbooks. He became interested in them again because he was working on a project about what happens when you take solid crystals, put them under an electric field, and see how they affect light. Essentially, would it change the absorption spectrum of solid crystals? And then after he did a bunch of those, he said, I wonder what would happen with liquid crystals. This is his experimental setup. Again, it's from his lab notebook. So what he does is essentially he takes a sample of a liquid crystal, he puts it in a sandwich between two glass plates with a transparent coating on either side, and that way he can apply a field across the sandwich, right? He puts that whole thing on a heated microscope stage and then sticks it between two polarizers, so you can view it with polarized light, and then he flips the switch and nothing happens at all. at first, because he ramps up the voltage. And as he ramps up the voltage, when the field reaches about 1,000 volts per centimeter, something weird happens. This is where the liquid crystal was without the field. This is how it looked when the field was applied. You can see a clear difference here, right? Well, so did he. And he noticed that this also blocked the passage of light. These weird rectangular regions, which he would later call domains, would block the passage of light. We now call them Williams domains in his honor. And they went away when he turned off the field. So this was reversible, again. If you're at RCA and you discover a new way to modulate the passage of light electronically, the first thing you think of is maybe this has a display application. And that's what Williams immediately decided about his crystals. He actually wrote up a patent and a couple of articles describing what he had found. But he found it difficult to persuade people that this was worth taking seriously because you had to heat up these liquid crystals that he was working with over 100 degrees Celsius. It's really hard to imagine filling an entire screen with that. Not to mention the fact that, again, this was not a widely known phenomenon, and this doesn't really look like an image, right? This looks kind of like a pattern. It's nice, but you're not really seeing a face or any sort of recognizable shape even here. So he sets it aside, goes on a sabbatical in Switzerland, and ultimately that would have been the end of the story had he not come into contact with George Heilmeyer, who was looking for something exactly like this. The liquid crystal molecules were clearly forming really regular patterns, right, when you applied a voltage. So maybe this would let him manipulate those dye molecules we saw a couple of slides ago. So he puts in one of these dyes, particularly one of the ones that can change its color depending on orientation. He calls that a guest dye, and he dissolves it in a liquid crystal host. And with the help of a technician named Louis Zanoni, he applies the conductive coatings in different patterns, and look what he's able to make. It's the RCA meatball. That was what they called the logo, the meatball, right? For obvious reasons. Okay? And this was pretty neat, and was enough to persuade Heilmeyer this had real possibilities beyond just lasers. In fact, he sets aside lasers pretty quickly to focus on displays. But this was not perfect. There were a limited number of dyes you could use. They required high temperatures again, which wasn't great for them. They tended to break down over time. And you needed polarized light. And polarized light, I don't know if any of you have ever seen a 3D movie lately, but you use polarized lenses there, it cuts out a lot of the brightness, right? So that means that it's not going to look nearly as bright when you make a display out of it. So Heilmeyer didn't like that. He wanted something that would not use polarized light, ideally. And he found a way to do it, with an effect that Williams had observed but not really pursued. It turns out that when you amplify the voltage even further, kick it up another order of magnitude, you can actually cause the domains to disappear, and it just turns into turbulence in the liquid crystal. And that turbulence, as it turns out, can scatter light. And if you applied coatings to the glass, you could even make that turbulence occur in regular, predictable patterns. So here's the glass without the voltage applied. Here it is with it on. All right, that's pretty striking. The reason this is here, by the way, is so you can get the contrast between the liquid crystals, black and white, and compare that with a printed page. And you can see it's pretty close. Right? This is called dynamic scattering. This is what ultimately persuaded Heilmeyer that he had enough to go to his managers and say, we should do something with this. And his manager said, yep, you're probably right, we should. So for the next 3 years, they embarked on a secret project. There was absolutely no publication from RCA between 1965 and 1968 about liquid crystals at all. The project consisted of more than just these 5 gentlemen, although they were all very important to it. They worked on a variety of different tasks, ranging from improved materials that could behave like liquid crystals at room temperature. That was a big goal. That was really the work of these organic chemists, Joel Goldmacher and Joseph Castellano. They worked on getting a theoretical understanding of what dynamic scattering was, and that's where Lucien Barton came into the picture, along with Heilmeyer and Zanoni. And they worked on building prototype devices, like the test pattern I just showed you, or this little display here. And this may not look like much, but I included it for a very specific reason. Remember Bernard Lechner, the guy whose face was on that screen a few slides ago? He built this. And what this is 2 lines, essentially, of a TV picture being switched at TV speeds. But each pixel is a liquid crystal display, and each pixel has a transistor or some other active switching element behind it. This is essentially the very first, what they call active matrix display. And if you've ever looked at a television or a cell phone or any other liquid crystal display today, it's using the same circuitry or very similar circuitry that was used originally here. This is essentially the ancestor of every liquid crystal display you've ever seen in terms of its circuitry. So this is all well and good. 3 years go by, they come up with this amazing stuff, and, well, now we're back where we started, right? They go public, and you can see the press was pretty excited about the idea of super thin TVs and instant blinds. They also really liked this picture here of Robert Lohman, another engineer associated with the project, comparing his wristwatch to the first ever liquid crystal clock. Now, this image is fascinating to me for a lot of reasons, one of which is that a few minutes after it was taken, that clock ceased to work. And that was pretty much the state of RCA's liquid crystal project at the time because, let's face it, these were prototypes. They needed help turning them into manufacturable products that consumers could buy. So they reach out to RCA's operating divisions, the people who were responsible for manufacturing within the company. And specifically to the semiconductor division, or the electronic components division in Somerville, New Jersey. They had been working on displays using light-emitting diodes, or LEDs, and they seemed like a good place to go to work with LCDs, if for no other reason than because the low power requirements of LCDs made them compatible with integrated circuitry, potentially, and that seemed like a good partnership to build upon in the long run. They start out with a relatively small group, just a handful of people, and eventually the group grows so big that they have to move to a warehouse in a nearby town called Raritan, where they proceed to try to figure out what they're actually going to use these materials to make. RCA is a little reluctant. They think this is great as a kind of publicity opportunity, but they're a little reluctant to commit any funds in the short term, so they force the group in Raritan to actually come up with external contracts to fund their first product lines. They go to a company called the Jervis Corporation, which is interested in mirrors, automobile mirrors, and they come up with a project where they can use dynamic scattering to diffuse the nighttime glare that you might see in your automobile rear view mirror. They go to a company called Veeder-Root, which specializes in gauges and meters, and they say, we can make you a gas pump readout. And then they go to a company called Ashley Butler, which is an advertising firm, and they see some possibilities in using liquid crystals in advertisements, like this one. Right? This is what's known as a point-of-purchase advertising display, and if you watch, you can see that it's a simple animation that you might put behind a bar to advertise whiskey. But think about all the things you had to do to make this work, right? Not only did you have to synthesize liquid crystals, and theoretically, if you're making a lot of these, you have to make a lot of liquid crystals, right? Not just little amounts you might use at the bench. You also needed to come up with a way to not just make simple patterns, but full-fledged whiskey bottles, theoretically. There it is, right? You have to figure out how to get that to switch on and off in a sequential fashion, and you have to make sure the display is sealed and rugged enough to transport. So all of these things they're working on at Raritan. There's still a sense within the division that the company doesn't quite know what it's doing when it comes to liquid crystals. There was a feeling that they just hadn't thought what kind of products they really wanted to make. Now that wasn't absolutely true. In fact, there had been some discussions within the company of what sort of products they could make in the first place. And in March 1970, they issued a licensing report, which is in the Sarnoff Library's collection. And this report had a bunch of different ideas, everything from dashboard displays to street signs to that electronic curtain down here to provide privacy with a push of a button, or even a flat screen TV, although they said at that point black and white was maybe possible, but definitely not color, not in the near future. They could imagine it happening, but not anywhere soon. But ultimately, even after they consulted with people like George Heilmeyer from Princeton and a couple of the managers from Raritan and marketing experts from New York City, they concluded that the technology had relatively little market potential, except for alphanumeric displays point-of-purchase advertising signs, and flat glass glazing. And if that sounds familiar, it's because the exact same three technologies were the ones they were able to get contracts for that I mentioned just a moment ago. Right? So this was bad. It seemed like this was the limit right now of what RCA was going to be in a position to manufacture. And it's possible that some of the other technologies that were being floated at the time, for example, in Raritan, they were talking about a liquid crystal display wristwatch, if you can believe that, right? It's possible they might have persuaded some of their management to agree to that. But there was also opposition from an unexpected source within Princeton itself, at the labs. Now, to give you a sense of this, I found a document that is, in my opinion, quite remarkable. This is a licensing report, the sort of thing that RCA would give to other companies that would want to manufacture liquid crystals and persuade them this was great and you should buy the right to use their patent. Okay? But some joker with a pair of scissors and some rubber cement decided they would change it up a little bit. So the title of the report was RCA Liquid Crystals, but look what they added to the bottom here. Be suspicious. Over here is a page on liquid crystal preparation, and they pasted in this advertisement of a goofy-looking scientist saying it's simple and idiot-proof. But the most damning comment, in my opinion, is this one. Advantages of liquid crystals. And right next to it, it says 4 words. Nixie tubes are better. Does anyone know what a Nixie tube is? All right. For those of you who don't, this is a Nixie tube. If you want to see what it looks like in person, this is a Nixie tube. Hopefully that turned on. Oh, there it goes. A Nixie tube was an early form of numeric indicator, essentially a neon bulb with 0 through 9 filaments that would go electronically be selected to register whatever you were measuring. They were big, they were heavy, they emitted light, so they were very inefficient in terms of power. They were encased in glass, so they're fragile. They're pretty much everything the liquid crystal display isn't, and someone's saying they're better. Now, did they actually believe that? Or were they just making fun of someone who did say that? Hard to say. I have no idea who made this. But what I do know is that it says that there was uncertainty about the technological potential of liquid crystals in September of 1971, which was not a good time for a technology to be on the ropes at RCA. And I'll tell you why. Because there was a new person in charge of the company. This guy, Robert Sarnoff, David's son. David Sarnoff had climbed up the ranks in the company, essentially starting as a wireless operator and going up through the technical side of the business. Robert Sarnoff started off as president of NBC and was very good at the sales and marketing side of the business. You can see he changed the company's logo. You can still see that on some televisions that are sold today. And his thought was that RCA was old-fashioned and should go beyond just being an electronics company. They should be a conglomerate. And they invested in companies like Hertz Rental Cars and Banquet Frozen Foods and Coronet Carpets. And people used to say that under Robert Sarnoff, RCA no longer stood for the Radio Corporation of America. It stood for rugs, chickens, and autos. Now, why was he doing that? Well, his answer was all of these side businesses were going to help RCA become a major player in the computer business. David Sarnoff had made his fortune in television, and Robert Sarnoff now wanted to make a name for himself and stake RCA's claim in computers. And to give you a sense of his ambitions, I have a brief video clip.
Did you ever wonder what your future will look like? How about trying this future on for size? Until now, computer advances have been made and measured in terms of what the computer could do for itself. Now we are in a decade of difference, a decade of what the computer can do for you. RCA has created the difference. We had to, because our man at the top, Mr. Robert Sarnoff, means business when he says RCA computers are going to be number 2 in the industry, with 10% of the market by 1975. Well, we decided to work things out anew.
Think about that for a second. His big goal was to become number 2 in the industry with a 10% market share. And you can understand why, right? Because there was already a very big company out there that was controlling the vast majority of the market share for computers. And you could spell it out in 3 letters: IBM. Now, early on, RCA thought that it might have a solution to this, which was to make its computers, like the Spectra 70 mainframe, compatible with IBM software. But the problem was, if IBM did something like, upgrade its computers, then that left your company struggling to catch up. And that was exactly what happened. So in 1971, because they couldn't afford to keep pace with IBM, they end up leaving the computer industry entirely. They sell off their division to Sperry Univac for $127 million. They called it the biggest business disaster since the Edsel. So this is in 1971, right when that technical report I showed you was being repurposed, shall we say, right? Which means that when there were major staff cuts, and there were major staff cuts at RCA in the wake of this sale, things that were on the borderline were among the first things on the chopping block, right? So there was a 10% budget cut, a literal decimation of the budget at RCA Labs after the computer crisis. 6 to 7% of the staff were fired. Some people left before then. George Heilmeyer actually got a White House fellowship and was able to land on his feet. Other people were transferred to other projects, and some people were laid off. At Raritan, it was even worse. According to one person I interviewed, there were 31 people on staff in 1971 before things went south with the computer business. Afterwards, there were only 8. Now, RCA continued to manufacture liquid crystals, but it was really hobbling along, and they continued to rely on external contracts for companies that wanted to kind of dip their toe into making numeric indicators or that sort of thing. But by 1975, Robert Sarnoff, who had somehow survived this computer crisis without getting kicked out, was finally laid off, and the new CEO of the company decided that something had to be done, so they sold the entire liquid crystal operation as part of their kind of house cleaning measure to Timex, which proceeded to start making liquid crystal watches. And that might be the end of the story, right? But it's not. Because if there's one thing I hope you've seen so far, it's that the scientists and engineers have a great deal of influence both in the success and also the failure of the product, right? In this case, they were involved in deciding, well, these are the products that liquid crystals were most effective at being used in, and they'd reached a kind of growing consensus that dynamic scattering, unless they were willing to pour in a lot more money, had reached a sort of limit in terms of its development. And after RCA ceased to really commercialize liquid crystals in a sustained way, they continued to influence, they being the scientists, continued to influence the industry, just not necessarily RCA. And I'll show you what I mean, right? Here's one particularly influential former member of the RCA research group. His name is Wolfgang Helfrich. He was a physicist who was in charge of figuring out how the molecules behaved inside of liquid crystals. And during the course of his research, he figured out an idea for a new kind of display that used a kind of liquid crystal staircase, a helical structure, to control the passage of polarized light. And he presented this, according to an interview I had with him, to Heilmeyer, and he says, I came up with this great idea. And Heilmeyer says, but it uses polarized light. And remember, he didn't like polarized light because it cuts back on the brightness. And they'd already invested a lot of money and time on making dynamic scattering displays. So he says, we're not going to work on this right now. Helfrich eventually leaves, gets a job at Hoffmann-La Roche in Switzerland, teams up with another physicist named Martin Schott, and they eventually construct what becomes known as a twisted pneumatic display. And if this looks complicated and unfamiliar, I'm guessing this doesn't. That gray and black numerical indicator that you probably have seen on every wristwatch and calculator that has a liquid crystal display, right? That's a twisted pneumatic display. It operates at lower power than dynamic scattering displays, and because it doesn't have a need to have a reflective backplate because of the scattering of the light, you get higher contrast. So it became more and more popular. In fact, every pixel on your liquid crystal TVs is a variation of a twisted pneumatic light shutter, essentially. So, RCA scientists are developing new technologies and influencing the broader industry that way. They also are starting up new firms, like this one called Optel, which ultimately made the first liquid crystal wristwatch years before Timex ever thought about doing it. And they were pretty quick, as you can see from these gray and black indicators here, these watch faces. They were quick to adopt new technologies too. Several core members of Heilmeyer's group would leave to form startup companies or become consultants in the industry, sharing their knowledge across the country. But perhaps the most important influence that the RCA liquid crystal group had was its capacity to persuade other innovators that liquid crystals merited sustained investment over time. And the best example I can find of this comes out of Japan in 1968. So in May of 1968, they have the press conference, and the press coverage is worldwide. This is a Japanese newspaper. It also shows up on TV, and it catches the eye of a gentleman named Tomio Wada, who's a chemical engineer who's working at the Hayakawa Electric Company. And Hayakawa Electric is trying to come up with a new portable calculator. And it's going great, except they can't come up with a display, because Nixie tubes take up too much energy, right? They're not going to work. They're too heavy. And they're too power intensive. There are other forms of display you could use, like electroluminescence, but none of them seem to be working well. He sees this and says, this might be the solution, right? Liquid crystals might provide us with a display for a calculator. So he goes to his boss, Tadashi Sasaki, and persuades him to go to RCA and ask if they'd like to team up. And Sasaki goes to Somerville, where they're working on liquid crystals, and he asks, would you like to partner? And RCA says, no. Thank you. But we'd be glad to license you our patents if you'd like. So, for around $3 million, Hayakawa Electric buys a license to work on dynamic scattering liquid crystals, and they start investing more and more money after that. And a few years later, they ultimately do succeed in creating their portable liquid crystal display readout calculator. But you probably haven't heard of Hayakawa Electric. I'm guessing you know by that point, however, that it changed its name to the Sharp Corporation. That's a name that's much more familiar. And it was the Sharp Corporation, after the success of this calculator, that would ultimately invest millions into liquid crystal manufacturing and produce David Sarnoff's dream of a full-color liquid crystal television. Exactly a century after Friedrich Reinitzer first observed the unique electro-optic properties of liquid crystals, engineers and scientists at Sharp built a 14-inch color liquid crystal display television. RCA by that point no longer existed. They had been bought by GE about 2 years earlier. But all the components that are in that television that make it work could trace their roots one way or another back to New Jersey. The room temperature liquid crystals, the twisted pneumatic shutters, the active matrix circuitry, the switching circuitry. All of those, in one way or another, emerged from RCA's laboratories in Princeton. The world of screens that surrounds us today, the one in which we live, testifies to the lasting influence of RCA scientists and engineers on the electronics industry, and the persistence of that influence even half a century after they unveiled their first dynamic scattering prototypes. And if you'd like to learn more about this, then might I recommend a book? It's called The TVs of Tomorrow, and it will be available wherever fine books are sold. So that's all I have to say about the topic. Thank you very much, and I look forward to your questions.
All right, raise your hands if you have a question. I'll come by with the microphone. We're videotaping and live streaming the program tonight, so we want to get the audio of your question for our worldwide audience. Just be sure to hold the microphone close to your mouth, otherwise.
Hi.
Hi.
My question is beyond this. How did all of this morph into high-definition TV? What's the difference in very simple ways? Because it sort of started around the same time these things came out. I remember seeing them at Sony.
So high-definition TV really comes out of a collaborative effort between actually the company that took over RCA's old labs. So RCA gets sold to GE in 1986. GE doesn't need two laboratories, so they sell one, they transfer the ownership of one to a company called SRI. That laboratory becomes essentially a research contractor that's involved in the development of the first HD TVs. And they work with a bunch of other American companies in what's known as a grand alliance to come up with a way to make very high-resolution pictures and also figure out a way to transmit that within the bandwidth restrictions that the FCC requires. So that's the short version. There are a couple of really good books on the subject that I can recommend.
Extremely interesting, which gets me to wonder, what are you currently researching?
That's a very good question. Well, honestly, I've been working on this book for so long, I haven't had a lot of time to pick my next project. I have a couple of ideas, but they're mostly revolving around electronics in the Cold War, just broadly, and particularly the consumer side. But I haven't really had a chance to catch my breath after the release of this book to start thinking about the next one. If you have suggestions, I would be open to them. Please let me know.
Did not the same thing happen with Bell Labs and then the transistor? Japan picked it up and made the first radio out of it?
Actually, it's slightly more complicated. If memory serves, the first transistorized radio was developed by Regency Corporation, which was a division of Texas Instruments. But there was a very big licensing arrangement between both RCA and Japan and Bell and Japan. And this really kicks into play more in the late 50s, early 60s. You do see that kind of situation happening. Now, what really doomed Bell, I would argue, is that they lost their state-sponsored monopoly. Bell had essentially de facto control over the telephone system. When that monopoly was taken away and the Bell system was broken up, then they couldn't afford to maintain their research labs. They had to think more about short-term profitability rather than long-term research. So that really was what doomed them. Now, in terms of the transistor, again, they weren't alone. Lots of companies fell victim to this. RCA did it too. But it was a similar situation, and I would guess there were similar dynamics at play in terms of how the scientists and the managers interacted with each other.
We had a question up front here. Rory, did you have your hand up? Yep.
I was just curious, when you were talking with the scientists that were working on the project, what were their reactions? Were they frustrated that they weren't able to capitalize it, or how did they feel about what they see now versus how they saw it play out?
It was mixed. Some people expressed some frustration. Most of them, though, said that they were pleased that they were there at the beginning, that it made them happy that they were able to go to an electronics store and see the descendant of the technologies that they had helped to pioneer really come to fruition. There's a lot of regret, I think, among the folks who worked at RCA, not just on this, but on lots of other things about the way the company ended up, because they had been around for so long, and they had such a storied history. But they also take great pride in that history. So if you ever run into someone who worked at RCA, they will tell you that they really enjoyed it, and they worked on some really fascinating projects, some of which I just didn't have a chance to talk about here.
Yes, sir.
Was this technology really feasible without the integrated circuits that were being developed at the same time?
Yes and no. When you say this technology, do you mean liquid crystal displays, or do you mean liquid crystal display televisions, or do you mean some other application? Because depending on your answer to that, it could vary, right?
I don't know whether it could vary. I just don't know whether the applicability of liquid crystal could be accomplished without integrated circuits.
Well, to give you a sense of this, they were able to make, before RCA got out of the business, there were people selling liquid crystal display wristwatches with integrated circuits as the drivers. So there was some capacity there. For television, however, that required scaling up over many, many years. That was why, although the displays were developed originally in the late 60s, it took until the 80s to get something that was big enough to actually look like a regular television. And that was due to advances in integrated circuit manufacturing, so you're right on that score.
Dr. Gross, thank you for a wonderful lecture.
Thank you very much, ladies and gentlemen.
I know you probably have a few more questions for him, but we're going to start the book signing soon, so you can ask your questions when you purchase your book. And Rainy Day Books will have copies of the TVs of Tomorrow for sale. And really, it's just a wonderful book, just a great read, very informative, and just a fun read as well. Just an interesting story, as you've heard tonight. So thank you for attending the program tonight. Pick up a flyer for our future events, and we hope to see you back here at the Linda Hall Library soon. Thank you and good night.
Thank you, everybody.
What I could offer